right, so today we're going to look at section 4.2. Okay, yesterday we looked at 4.1, which kind of introduced us to rational functions. Today we'll do part of 4.2, which is how we graph them. All right. So one important thing we want to remember is when you can have a hole in the graph. Right? And that can happen if the numerator and the denominator have a common factor. And the reason you need to recognize that is because the calculator won't show it to you. Right? You can zoom in, but you won't see it. Right? We're going to just look at two quick examples of graphing things that have holes in them. All right? We'll try graphing this one. X minus 1 divided by x minus 1. Now, first thought might be, well, the denominator is going to have a problem at 1, right? Because that'd be a divide by 0. And usually that's a vertical asymptote. And it would be, except look at the top. The top has the same factor as the bottom. So what's going to happen here is we're basically going to get these two things cancel each other out. Okay. David, what do you get when you divide two things that are the same? 1. So basically this is going to look just like this. Except there's going to be a very, very small hole in the graph. Right? So let's graph it. So we'll put it in parentheses, x minus 1 divided by x minus 1. So basically it's a horizontal line, like y equals 1. Except, where is the hole here, Devin?
When x equals 1.
When x equals 1, we have a hole. Okay, if we try to trace to 1, notice it says there's no y value. You can go very, very close to it. You can do 0.999999. That's fine. You can also do 1.000001. That's fine. You just can't do 1. So it's like an infinitely small hole, just at when x equals 1. All right? Now, when we graph this one, right, the way I would think of the denominator, think of it as that whole factor as having an exponent of 1. What would that simplify to? What do you do with these exponents when your bases are the same?
You just subtract 1 from 2.
Yeah, you just subtract them and you keep the base the same. So basically this graph is going to look like that. It's going to look like a line with a slope of 1, y-intercept at -1. Except it's going to have a hole when x is 1. All right, so if I graph that, you can just use the last one and just make the numerator squared. Hit graph. And there's my graph. Okay, now if I graph y equals x minus 1, you won't see a difference on the screen. Put that one right below it. It's going to trace right over it. But we have to know there's a hole there. Okay? So what I would do is if we were sketching this on paper, you could just put an open circle right on 1, like this. And leave it not filled in. So kind of draw your line up to the circle, leave it open, and then continue drawing your line. Okay, questions on that? So in example 1, we didn't have any vertical asymptotes. We had a discontinuity. Okay, we had a point where if we were going to draw this with our pencil, we would have to pick our pencil up and start drawing again. So it is not a continuous function. But it's a removable discontinuity, meaning if you could just redefine that one point, you could make it continuous. All right, so all we'd have to do is say, you know what, we'll just redefine when you let x equal that one value, what y should be, and then boom, get a continuous line. Right? So that's called a removable discontinuity. Just another name for a hole in the graph.
Please excuse this interruption.
Okay, questions on that idea? All right. All right, so suppose we had a rational function. Okay, all that's represented here is the top would be a polynomial. Think of it as like 3x cubed plus 2x squared plus 5x plus 7. Right? And then the bottom would be another polynomial. Okay, we talked, I think it was last week, about the EBM, or the end behavior model. Okay, to find an end behavior model, all you have to do is look at the term with the highest exponent. Okay, that's the term that controls everything. Right? All the other terms might cause like little twists and turns, but that's what's going to control the behavior of the top. That's what's going to control the behavior of the bottom. So the first term here is an end behavior model for the denominator. The first term in the top, that's the end behavior model for the numerator. Well, if we want to get an end behavior model for the entire rational function, all we got to do is take the end behavior model of the top and divide it by the end behavior model for the bottom. And now we have an end behavior model for our rational function. And what this is going to allow us to do is figure out what is happening as x gets really big. But it ignores all the stuff we don't really need to think about. It just looks at the most powerful term in the top and the most powerful term in the bottom. Right, so remember, for polynomials, the kind of things that usually happened is it either went towards infinity or negative infinity. Whether it was both ends towards infinity, both ends towards negative infinity, or one up and one down. Okay? Usually what's going to happen with rational functions, okay, is the end behavior model is going to head towards a number. Could be 0. Okay? It depends on the problem. Right? And we already used this idea earlier, but if you're going to divide two things and you've got the same base, subtract your exponents. Right? So if you had something like 3x to the 4th divided by 9x to the 1st, say this was the leading term in the top, that's the leading term in the bottom, this would reduce to 1/3 x to what power, Dave?
Third.
Yeah, 4 minus 1 is 3. That would be the end behavior model. Okay? All right, so let's try this one. Okay, find the end behavior model for this rational function. Devin, what term in the top is really going to control everything that's happening?
2x squared.
Yeah, this minus 1 doesn't even really make a difference. Okay? 2x squared is what's going to control pretty much everything. Okay, and Dave, how about in the bottom?
3x cubed.
Yep. Now, if you want the end behavior model, take the one for the top, divide it by the one in the bottom. So my end behavior model is 2x squared divided by 3x cubed. And Devin, what will that reduce to?
2/3 x to the -1.
Yep, perfect. 2/3 x to the -1. And Dave, do you remember what that means when you have x to the -1? Where does the x really go?
I don't remember.
Do you remember that, Devin?
Wouldn't it be 1/2/3 x? Or is it 1 over something?
Yeah, 1 over x. Okay, so
Yeah.
x to the -1 is the same as 1 over x. Okay. X to the -2 would be the same as 1 over x squared. Okay? So in this case, you can write it as 2 over 3x. Right. So anytime you have a negative exponent, just put it in the bottom. Okay? That's your end behavior model. Okay. Any question on that? All right. Now they also want us to find horizontal asymptotes. Okay. To find a horizontal asymptote, use your end behavior model and let x get really big. Okay? And as x gets really big, tell me what happens to that fraction. All right. So Dave, what's going to happen if I let x get really, really, really big and I put it in the bottom and multiply it by 3, and then do that out. This fraction will get really big?
Yes. Well, right, are you doing the division or?
Yeah, if you do the division, yeah.
It would get smaller.
Get very small. All right, so if x was like 1,000,000, plug it in, you'd have 3 times 1,000,000, that's 3,000,000. 2 divided by 3,000,000 is extremely small. And it's getting closer and closer to what number really? Debbie? 0. So your horizontal asymptote here is at 0. Same thing happens if you go towards negative infinity. It'd just be like 2 divided by negative 3,000,000. Still very, very small. Right? Okay, Dave, what's my end behavior model here? Before you simplify it.
2x to the 4th or 3x to the 4th.
And Devin, what's going to happen with these x to the 4ths?
They cancel.
Yeah, if you subtract the exponents, it's like you'd have x to the 0, which is just 1. That's my end behavior model. Okay, 2/3. Okay, any question on that one? All right, so now as far as the horizontal asymptote, okay, you do the same thing. Let x get really, really big and tell me what this fraction approaches. Well, do I have an x in that fraction? No. So as x gets really, really big, what happens to this fraction? What does it approach?
It doesn't change.
It doesn't change.
Yeah.
So it just approaches 2/3. That would be your horizontal asymptote. Okay, so sometimes the horizontal asymptote approaches 0. Usually happens when you have a variable in the denominator. Or if all your variables cancel out, your horizontal asymptote approaches that number. Okay. All right. Any questions on that one? All right. So now for the last part, all we're going to do is try to make some sketches. Okay? Sketches can be a little tricky because sometimes you've got multiple asymptotes, but I'll show you how. I'll give you some suggestions. Okay, specifically, these are the ones we're going to graph today, where the degree of the numerator is less than or equal to the degree of the denominator. Okay, that's just like the last two. Okay, in example 2a, the degree of the numerator was less than the denominator. In example 2b, the degrees were equal. Tomorrow, we'll look at what happens when the numerator is bigger. That's a little different. Okay, but here's some suggestions of things you can try to find. You can always look for intercepts. Okay, if you can find your x and your y-intercept, that'll help make the graph. Find vertical asymptotes. Okay, we're going to put those in as dotted lines. Okay, find your end behavior model and use that to find the horizontal asymptotes. Again, we'll put that in as a dotted line. Okay, once we have the vertical asymptote, we're going to use the graphing calculator to evaluate our function on each side of the vertical asymptote. So what we'll do is, say you got a vertical asymptote at 2. Okay, we'll check what happens as we get very, very close to 2, like 1.99 and 2.001. Okay, we'll just check the behavior, and that'll help us make part of the graph. And the last thing we can do is just confirm with a graphing calculator. Okay, so we'll just try 2 or 3 examples of sketching a rational function, and that'll be it. Okay, and we can come back to these steps if we need to. Okay, does anyone need more time to copy these down? Okay. All right, so that's our first one we'll sketch. X minus 1 divided by x squared minus x minus 6. Okay, if you have lined paper, that'll be the best thing to use for now. If not, I can see if I have any graphing paper. All right. So first thing I would find, let's go back to the directions. Okay, let's start with our asymptotes. Okay, you don't have to do these in any particular order. But I usually like to find the vertical and horizontal asymptotes first. All right. How do we get our vertical asymptotes? Remember how we get those?
When the denominator equals 0.
Good. When the denominator equals 0, as long as this x minus 1 is not a factor in the bottom. If it is, we'd have a hole there. Right? But I don't think x minus 1 is going to be one of the factors. Okay, if we factor the bottom, it's going to factor with a 2 and a 3. And let's try minus 3 plus 2. Okay, x squared minus 3 plus 2 is minus 1. And 2 times negative 3 is negative 6. Good. So we've got 2 vertical asymptotes. Dave, what are going to be my 2 vertical asymptotes?
X equals negative 2.
Yep. Positive 3. I'm going to draw those on my graph. Okay, vertical asymptote at negative 2. And another vertical asymptote at 3. Okay, so there's my vertical asymptotes. Let's find horizontal asymptotes. Okay, to do that, we need the end behavior model. Okay, in this case, Devin, what's the highest, or what's the most powerful term in the top?
X.
Yep. And the bottom?
X squared.
X squared. And what does that reduce to?
Just 1 over x.
Good. And what's going to happen as you let x get really, really big in that fraction, Dave?
It's going to get really small.
Yep, and it'll approach what number?
0.
0. Okay, so now we've got a horizontal asymptote at 0. Okay, so let's put that in. All right, you can kind of see how we're breaking this up. We're going to have different sections, okay, of the graph. All right, what else? All right, so we've got that. We'll do the evaluation in a minute. Let's see if we can find the intercepts. All right, to find the X-intercept, that's when you let y equal 0. Okay, so X-intercept, basically when you set this fraction equal to 0. Well, what's the only way this fraction could equal 0? If what was 0? Devin, how do you make a fraction equal to 0?
You said the numerator equal to 0.
Yeah.
So
Denominator doesn't matter. It's just
Yeah.
as long as the numerator equals 0. 0 divided by anything is 0. Right. So if we set y equal to 0, y would equal x minus 1. Right? Or 0 equals x minus 1. What's my x-intercept?
1.
Yeah, x-intercept is at 1. Or if you want it as a location, there it is. Right, so that's a point we can put right on the graph. My graph goes right through that point. Okay, and the other thing we could try and find is the y-intercept. Okay, so the y-intercept, that's easier. That's just when you plug 0 in for x. And evaluate it. Well, if we plug 0 in the top, Dave, what's 0 minus 1? Negative 1. 0 squared?
0.
Minus 0?
0.
Minus 6.
Negative 6.
Negative 6. So your y-intercept is going to be at 0, comma 1, 6. Right, so just above the origin. All right. Now what I'm going to do is type this into the calculator, and I want to investigate the behavior on each side of this asymptote. All right? So let's type it in. We got x minus 1 divided by x squared minus x minus 6. All right, so x minus 1 divided by x squared minus x minus 6. Okay, I want to make sure that under my table setup, my independent is on ask, my dependent is on auto. Okay, let's start with this asymptote on the left. Devin, what's a number that's very, very, very close to negative 2?
Negative 1.999.
Sure. So just to the right of it, negative 1.99999. If I plug that in, okay, what's happening to y?
It's getting really big.
It's getting really big. Okay, so what's happening here is this graph is going to curve up very, very sharply. Okay, now we want to check the behavior just on the other side of that asymptote. Dave, what's a number that's just on the other side of the asymptote?
2.00001.
Positive or negative?
Negative.
Yeah. Negative 2.00001. Okay. What's happening if I plug that in?
Gets really big, or really small.
What's it heading towards? That says negative 60,000.
Oh, I read it backwards. That's getting close to negative 2.
Well, our x value is just to the left of negative 2, but what is y approaching?
Oh, 1 or negative 1.
It's a lot lower than that. Right now it's at negative 60,000. Let's try a number like negative 2.0000001, even closer. Now we're at negative 600 million.
Oh, it's just going up to infinity.
Yeah, negative infinity.
Oh.
All right, so this is dropping off way down here to negative infinity. All right, now we're going to do the same thing at 3. Check the behavior on each side. All right, so I'll check, say, let's do 2.999. Okay, or if you want to go even closer, you can, but I think we get the idea. At 2.999, it's heading towards negative infinity. Okay, negative 400. Okay, and then on the other side, it should be heading towards positive infinity, but let's just check 3.001. Okay, and it's up at 400, so it's heading way up. All right, so that's enough information to make the graph. All right. We know we have a horizontal asymptote at 0. All right, so what's happening is our graph is going to start here, and it's going to get closer and closer to this horizontal asymptote. But remember, it's not going to cross it as it goes way out. So it's going to look something like that. It has to stay between those dotted lines, and it gets closer and closer to each one. Okay, same idea is going to happen in the upper right section. It's going to go from here to here. It's got to stay between those asymptotes, but it has to get closer and closer to each one. So it has to curve something like that. Now in the middle, we pretty much just want to connect all those dots. But don't connect them straight. Connect it as curved as possible. All right, so that's getting closer and closer. It's going to go right through those 2 points. And then it's going to come down like that. And that's your graph. And that's the basic idea of graphing all of these. We can double check it. Zoom 6. And that's basically the picture we get. Same thing we drew. That's it. That's all there is. That's how you graph a rational function. Okay, any questions on that? All right, so we'll try, let's see, how many more do I have? 1, 2, 2 more. So if we want to do both, we can. If we only need to do one and you guys want to try one on your own, then that'll be it. All right. So I kind of laid this one out for you. Find your asymptotes, then find your intercepts, and then I got room for the graph. Okay, vertical asymptotes. Dave, how do I get my vertical asymptotes?
You set the bottom to 0.
Yep, perfect. You're going to set the bottom to 0. Okay, they both have an x, so I'm going to factor that out. And now we have two factors. Devin, what would make this first factor 0?
0.
Yep. And Dave, what would make this second factor 0? Think about if you set that equal to 0 and then solved it.
5 halves?
Yeah, perfect, 5 halves.
That's in my head.
Yep, for graphing purposes, we might want to use 2.5 just so we know where to put it, but that's perfect. All right, so let's put those in right now. 0, 2.5. So there's 0 and 2.5. Okay, let's do our horizontal asymptote. Devin, what do I need to do the horizontal asymptote? I find the what? It has 3 letters.
Oh,
Yep, and behavior model. All we want to find out what's happening to the behavior at the end of the function. Okay, Dave, what's the end behavior model for just the numerator?
3x squared over 2x squared.
Yep, so numerator 3x squared, denominator 2x squared. And what does that reduce to?
3 halves.
Yeah, the variables cancel out. So when your degree of your top and the degree of the bottom are the same, what's going to happen here is it's going to approach a value that's not 0. Okay, we're going to have a horizontal asymptote at 3 halves, or 1.5. Same basic picture though. Okay, just the horizontal asymptote is shifted up a little bit. Okay, let's find our intercepts. Since we have an asymptote right on the axis, it might be possible we don't have a y-intercept. Right, let's see. All right, so the y-intercept, that's when you let x equal 0. Well, I can do that in the top fine. 0 squared is 0, times 3 is 0, plus 0 is 0, minus 4 is negative 4. But what happens if I plug 0 in the bottom? I get 0. Can I do that? No. So because you can't plug in x equals 0, which is how you'd find a y-intercept, because you divide by 0, there's no y-intercept here. This graph will never cross the y-axis. Okay, to find the x-intercept, that's when you set that side of the equation equal to 0. We've already said the only way a fraction could equal 0 is when the top equals 0. So set 0 equal to 3x squared plus x minus 4. Any questions on that? If we can factor that, let's try and see. If we can't, we could always use the calculator or quadratic formula. So we have 3x and x. Okay, we're going to have 1 and plus, 1 minus. And we could try 1 and 4. Let's see. Gives me 3x minus 4x. Is that what I wanted? No, just switch the signs. Let's try this. Now we get negative 3x plus 4 is 1. Yeah, we're good. Okay, so now find your x-intercepts. So it looks like we're going to have 2 of them. Okay, let's see how that's going to work. So we've got negative 4/3. Okay, comma 0. So I can write it like this. And I'm going to get another one when x equals 1. All right, so that's negative 1.3. And positive 1. Do you guys see why we could get 2 here? The shape it could make if it's going to curve, and then you have like a curve in the middle. It could cross the x-axis twice. Right, last thing to do is investigate the behavior on each side of the asymptote. So let's type in our function and see what happens. All right, so we'll type it in and see what we get. So we get 3x squared plus x minus 4 divided by 2x squared minus 5x. Okay, Devin, what would be a value just to the left of 0?
0.0001.
That'd be good for the right. Okay, we can.
Negative.
Yeah, we can use that other value in a minute. So if you go just to the left of 0, you're heading towards negative infinity. Right, so you're way down here. Okay, just to the right of 0, positive infinity. Okay, Dave, what would be a good value just to the left of 2.5?
2.4.
I would go 4.9. Yeah, just go really close to it. All right, and then we're at negative infinity. And what would be a good value to the right of 2.5?
2.5, 1, or 0.0001.
Yeah, anything very, very close to it like that. And which direction are we heading this time?
Towards infinity.
Towards infinity. All right. We know as it curves down, it's going to approach that asymptote. As this one curves up, it's going to approach that asymptote. Right, so now we'll make our sketch. So this one is going to come, curve down, just like that. Okay, that upper right section is going to do pretty much the same thing. Be kind of like an L shape. I'm not going to be picky about the curve, how you draw it. I'm just going to be looking for the basic idea. And then in the middle, well, it's got to get closer and closer to the right at the bottom and closer to the left towards the top, and it's got to go through that point. So it's going to do kind of a S shape in the middle. Okay, something kind of like this. I'd say that's what the sketch should look like. Let's take a look. Okay, and is that pretty much what we got? Yeah. Notice as the graph starts to get really, really steep, the calculator has a hard time drawing it because it's almost vertical, but the blue line does not stop right there. Okay. Any questions on that one? All right. So this is another one that's pretty much the same type in the book. Do you guys need me to go through one more of those?
Not mostly.
What's that? You good? Okay. There's nothing new here. In fact, this one has the bigger exponent in the bottom, so it's going to be similar to the first one we did, where you get that horizontal asymptote at 0. Yep. All right, so that's basically how we sketch rational functions where the degree of the numerator is less than or equal to the denominator. Tomorrow we'll do it where the degree in the top is bigger. Okay, we'll look at that tomorrow. All right, so the homework, it's on page 234. Okay, 1 to 7 odd, 9 through 12, 15, 17 to 22, 23 to 26, 29, and 33. Right, so we'll take a look at that first thing tomorrow, and I'll put some graph paper out in case you need that for the homework. All right, so for those people that are still watching, I will show the last example that we didn't do in class. This example is very similar to the first one where the degree in the bottom is bigger than in the top. All right, so first thing I'll do is find my vertical asymptotes. And I'll do that by finding the zeros of the denominator. Okay, if I can factor it, that generally makes it a lot easier. So we try x and x. Okay, two numbers that multiply to give me 3 are negative 3 plus 1. Let's check it. We got x squared minus 3x plus x is minus 2x, and 1 times negative 3 is negative 3. Okay, so we're going to have two vertical asymptotes. Okay, from the first factor, x would equal -1. From the second factor, x would equal +3. Okay, so we'll put those on our grid. -1 and +3. Okay, next we'll find our horizontal asymptotes. And to do that, we get the end behavior model. In this case, the highest degree term in the top is x. Highest degree term in the bottom is x squared. And when we reduce that, it becomes 1 over x. So as x gets really big or heads towards infinity, we'd have 1 divided by a really, really big number, which comes out to a really small number, approaching 0. Okay, so this time we have a horizontal asymptote at 0. Okay, next I'll find my X-Intercepts. Okay, the X-Intercept is when you set y equal to 0, or basically just let the numerator equal 0. So in this case, it'd be 0 equals x minus 2. Or in this case, my X-Intercept is 2, 0. Okay, and last thing I'm going to graph for a point is my Y-Intercept. Right, the Y-Intercept is when we plug 0 in for x. If you do that in the numerator, you'd have 0 minus 2, which is -2. In the denominator, you'd have 0 squared is 0, minus 2 times 0 is 0, minus 3 is -3. Okay, so my Y-intercept is at 0, 2/3. Okay, since we have a negative in the top and a negative in the bottom, they cancel out and become positive. All right, last thing I need to do is investigate the behavior on each side of the asymptote. So I'll type in my function, x minus 2 divided by x squared minus 2x minus 3. All right, so my first vertical asymptote was at -1. So we'll check a value just to the left. Okay, and we're heading towards negative infinity. Okay, we'll check a value just to the right, but we should be heading towards positive infinity. Okay, and we are. Now I'll check on my other asymptote, it's at 3. So I'll check a value just to the left of that, like 2.9. Right, we're heading towards negative infinity. And then check a value just to the right of 3 would be like 3.001. And we're going towards positive infinity. Okay, keep in mind that the curve has to get closer and closer to the asymptotes. Okay, on each side. Right, so your left section, looks something like that. Okay, the upper right section will look like that. And that section in the middle has to go through all the points I have drawn and get closer and closer to the asymptotes. Okay, so we get that standard kind of S curve in the middle. Okay, let's compare that to our graph. Okay, again, looks pretty good. So that's how you do the last example. And again, here's the homework that's due tomorrow.